You know that phone in your pocket? The computer on your desk? Well, inside all of them, and even in the critical systems that run our world, there's a hidden battle being waged. It's this high-stakes, microscopic war fought on tiny battlefields of silicon. And it affects, well, everything, from your privacy to global security. So, how is this secret war being fought? Let's dive in.
And this isn't just some theory. It is happening right now. Despite all the sanctions, sophisticated Western technology keeps showing up in military hardware where it absolutely should not be. This one quote, it just rips the curtain back on a dangerous shadow world of illicit trade and technological theft.
So that really leads to two crucial questions, right? First, how are these incredibly complex supply chains and sanctions being bypassed? And second, on a more basic level, how is it even possible to copy something as ridiculously intricate as a modern microchip? In this explainer, we're going to pull back that curtain.
To really understand how this happens, we need to zoom out and see the big picture. This isn't just about a few bad actors. Nope. This is a global issue, and it's being fueled by everything from supply chain chaos to geopolitical tension.
What we're looking at here is the recipe for a perfect storm. So you've got global chip shortages that create desperation. That desperation, well, it swings the door wide open for counterfeiters. And they've built these incredibly complex networks to move these components around, evading sanctions. And get this, many of these fakes are literally just pulled from e-waste, cleaned up and sold as brand new. It's a massive risk for, well, for everyone.
So, how do you copy a chip? You stage a heist, a microscopic, super high-tech heist. And the goal isn't to steal gold or diamonds, but something way more valuable in the 21st century, intellectual property.
The official term for this kind of heist is reverse engineering. It's basically the process of taking something apart to figure out how it works. I want you to imagine trying to recreate a city's blueprint, not from the original plans, but by painstakingly documenting every single brick, every wire, and every pipe. That is what's happening here, but it's on a nanometer scale. It's just wild.
In this slide, it's the 5-step playbook for the heist. It all starts with decapsulation. That's just getting the chip out of its plastic shell. Next up is delayering, where they shave off layers thinner than a human hair, one by one. Then you've got the imaging stage, using incredibly powerful microscopes. After that comes annotation, where every single transistor and wire is identified. And finally, all of that information is digitally stitched back together to extract the netlist, which is basically the chip's stolen blueprint.
The heist kicks off with a little bit of chemistry. What you're seeing here is step 1, decapsulation, happening in real time. That's a carefully controlled acid bath that's literally dissolving the black plastic packaging, all without damaging the unbelievably delicate silicon die at the heart of the chip.
And this is the prize. With that protective casing gone, the silicon die is exposed. I mean, it looks like a tiny, beautiful, intricate jewel, but it's actually a city with billions of transistors. And it's holding all the secrets that the attackers are after.
So how do you actually pull off this kind of heist? Well, you need a very, very specialized toolkit. Attackers have developed this whole range of methods, from straight-up brute force to techniques that are almost ghostly in how subtle they are. So researchers have broken these physical attacks down into 3 main categories. First, you've got your non-invasive attacks, which are kind of like listening in from the outside. Then there are semi-invasive attacks that might involve poking the chip a little bit. And finally, you have the fully invasive attacks, which are basically the equivalent of performing open-heart surgery on the silicon itself.
This table gives us a great at-a-glance comparison. A non-invasive attack, for instance, is cheap and it won't damage the chip, but you might not get a ton of information. On the other end, an invasive attack can get you everything, but it's going to be expensive, it requires unbelievable expertise, and yep, it completely destroys the chip in the process. So let's focus on that most extreme category for a second. Invasive attacks. This is where things get really, really wild. We're talking about performing surgery on a scale that is almost impossible to imagine.
I mean, just look at this. On the left, you see a diagram of something called a focused ion beam. Think of it as a molecular sandblaster, drilling a perfect hole through all the metal layers of a chip just to access a single wire. And on the right, that's not a diagram. That is a real image from an electron microscope of nanoprobes, probes that are smaller than a single bacterium, making physical contact with the transistor to read its secrets. The precision is just, it's breathtaking.
Okay, now for something even more subtle. This is basically a form of electronic eavesdropping.
As transistors on a chip flip on and off, they actually emit a tiny, tiny number of photons, particles of light. With super-sensitive cameras, you can capture this light. In these images, every little flash you see is data being processed. An attacker can literally analyze the pattern of these flashes to figure out what the chip is doing, all without ever touching it.
Faced with these absolutely incredible attack methods, you can bet that chip designers are fighting back. They're locked in this constant cat-and-mouse game, building what are essentially digital fortresses to try and protect their designs.
Two of the cleverest defenses they use are called obfuscation and camouflaging. With obfuscation, designers just add a bunch of confusing or useless logic to make the blueprint unreadable. With camouflaging, they go a step further. They make different components look physically identical under a microscope, so an attacker can't tell a plus gate from a minus gate just by looking at it. But of course, both of these techniques add complexity and cost, and that's the constant trade-off: security versus price.
Designers also use active defenses. One of the most powerful is the active shield. The best way to think about this is like a digital burglar alarm. It's this fine mesh of live wires laid over the most sensitive parts of the chip. If an attacker tries to drill through it, they break a wire, which instantly triggers an alarm that can erase the very data they were trying to steal. Pretty clever.
But, the battle just keeps evolving. While designers have been so focused on protecting the top of the chip with these shields, attackers have realized that the bottom, the silicon substrate itself, is often way less protected. And this has opened up a whole new and very dangerous frontier of what they call backside attacks. So let's zoom back out. This microscopic cat-and-mouse game of attack and defense, it might seem abstract, but its real-world consequences are absolutely enormous.
So why does all this matter so much? Well, first, there's the theft of intellectual property. Companies spend billions on R&D for these chips, and piracy can just cripple innovation. But the stakes get so much higher. Think about your safety. Counterfeit chips have been found in critical systems like medical devices and even the brakes of high-speed trains. And then there's national security. A single compromised chip in a power grid, a satellite, or a missile guidance system, well, that represents a catastrophic vulnerability.
The scale of this problem is just staggering. According to industry estimates, the annual cost of counterfeit electronic parts to the semiconductor industry is over $100 billion. That is a massive hidden tax on both innovation and security.
And that leaves us with a final, kind of unsettling thought. The very device you're using to watch this right now, it contains billions of transistors, all sourced from this incredibly complex global supply chain. This secret war for control over those tiny components is invisible, but it's truly one of the most important battles of our time. So the question really is, how can we ever be sure who made them all and what they're really doing?